Hello students, welcome to today's lecture on artificial neural networks. Today we will be starting the third unit. Third unit is all about what is a perceptron and how perceptron neural networks can be designed for a given set of problems. Okay, so these are the contents in third unit. Uh, the first topic is introduction to single layer perceptrons. Then we'll look into uh, structure of a perceptron and then how learning happens in perceptron. Then the next topic is what is meant by pattern classification, and we'll see a kind of classifier called as naive Bayes classifier. And then we go through how perceptrons can be used as pattern classifiers. We'll look into some examples, and then uh, we'll see how perceptron can act as a pattern classifier. To design, we make use of the perceptron convergence algorithm, and finally, we will discuss about some limitations of perceptrons. The definition is perceptron is the simplest artificial neural network. A single neuron can be called as a perceptron, which is basically used for classification problems. Okay. And it is not actually suitable for all kinds of classification problems. It is suitable only if the input patterns can be separated as linear separable patterns. Okay, so if the input patterns are linearly separable, then we can make use of a perceptron neural network for solving it. If you look into the structure, this is structure of the perceptron. The perceptron consists of a single neuron, some adjustable weights, and a weight bias. Because a neuron is consists of a summation function and an activation function. In mathematical terminology, a perceptron can be described uh, as the induced output can be calculated with the formula Vk is equal to summation of I is equals to 0 to m xi into wi, where xi are the inputs and w are the interconnection weights. Then actual output is calculated by forwarding this induced output to an activation function. You can take any activation function based on the application domain. For example, we can go with a signum activation function, which is also called as bipolar step function. If you observe this formula, W0 and X0 are also included. X0 is always going to be 1, and W0 acts as the bias weight. So bias is not separately taken, it is included as W0, and X0 acts as 1. Let us go through this learning algorithm used in perceptrons. This is an important topic for your examination point of view, which will be asked as what is perceptron learning algorithm, or perceptron learning rule, or perceptron convergence algorithm. It can be asked like that. The first step of any learning rule is to initialize all the weights of the corresponding network. So here also we'll follow the same step. Initialize all the weights of perceptron network to 0, including bias. Here we are mentioning W is equal to 0 for every I value 0 to m, where m is the number of connections or number of inputs. Wi starts with I is equal to 0, which will be taken as bias weight. W0 is taken as bias weight, as I told you earlier. And in step 2, we will calculate the induced output, the actual response of the perceptron. Y of n is equal to signum of x of n into w of n for each input x of n. Okay. The signum function can be defined like this. We already saw this signum function as bipolar step function. Signum of Vk, where Vk is the input, is going to be plus 1 if Vk is greater than or equal to 0. Otherwise, it will be minus 1 if Vk is less than 0. In step 3, we will calculate the new weights. W of n plus 1 is equals to W of n plus eta into d of n minus y of n into x of n. Here, W of n plus 1 is the new weight we are calculating at time step n plus 1. W of n is the old weight at time step n. Eta will be initialized at the beginning. We consider it as learning rate. D of n is the desired response from the perceptron, and Y of n is the actual response from the perceptron after calculation, and X of n is the input at time step n. Okay. What you need to understand here is if the desired response and the actual response are same, then this d of n minus y of n is going to be 0. Therefore, this entire term becomes 0. Therefore, the new weight is same as old weight only. So the weights will be updated only if there is a difference between desired response and actual response. Otherwise, weights will not be updated. Okay, so remember that point. It will be helpful while solving the example problem. Step 4 says that repeat steps 2 and 3 for all the time steps starting with 1 to infinity. Why the end value is given, not given is we don't know how many iterations will be required. The steps will be continued until there is no difference between desired response and actual response for every input vector given. That means if the perceptron classifies every input into a proper class, then we can stop the process. Otherwise, the process will be continued. Okay. Let us understand the process of perceptron convergence with the help of an example, a simple example we will consider. Look at the table. There are two classes of fruits available, fruit 1 and fruit 2. First fruit, that is fruit 1 class, has two samples over here. First sample is 121 grams weight and the length is 16.8 centimeters. And the second sample is 114 grams weight and 15.2 length centimeters length. So these two belongs to fruit 1 class. Fruit 2 class also has two samples. The first sample is 210 weight, 210 grams weight and 9.4 centimeters length. Second sample is 195 grams weight and 8.1 centimeters in length. Okay, so by considering this data, we need to build a perceptron network for classifying these fruits into either class 1 or class 2, and also the perceptron must be able to classify any other fruit given into either class 1 or class 2. Okay. After training, we can check whether it can test all the given fruit classes into their corresponding class. So design a perceptron classifier for identifying the class of given fruit based on its weight and length. Also identify the class of fruit. This is a class after designing the perceptron. You are given a task that 140 grams weight and 19.7 centimeters length fruit belongs to which class. You need to identify it with the help of the designed perceptron. So as it is given here, based on its weight and length, so there are two inputs required. Weight is one input and length is another input. And also we'll consider a bias, the third input. Okay. Now first thing what we need to do is we need to test whether the input patterns are linearly separable or not. If they are linearly separable, then we make sure that we can design the perceptron classifier. Otherwise, it is not possible to design a perceptron classifier. Just take a hyperplane representing the lengths and weights and represent the points given that C1, C2, and so C1. There are two points given. Which are, the first point is 121 comma 16.8 and second point is 114 comma 15.2. So 121 comma 16.8 and then now 114 comma 15.7. These 2 points are represented over here, and then remaining two given as 210 comma 9.4, 195 comma 8.1. You can represent them 210 comma 9.4 and 194 comma something over here 7 point value. So these two come over here. We can say that the input patterns are linearly separable if we can draw a straight line to separate the class 1 onto one side of the line and the class 2 onto other side of the line, and it is possible that we can draw a line anywhere over here to separate class 1 and class 2 input patterns. Therefore, the given input patterns are linearly separable, and we can design a perceptron classifier. Okay. Now, let us assume few things over here to design to start design the perceptron. The first two categories are assumed as +1 classifiers. So that means the desired response is +1 we assume. So +1 represents class 1 fruit, and the desired response is assumed as -1 for the second category of fruit, class 2. Okay, these are the desired responses assumed, and then we need to assume the learning rate also. Eta is equal to, we assumed it as 0.5. You can take any value between 0 and 1, right? And let us start the process. In step 1, we will initialize all the weights to zeros. So that is done over here. In step 2, we'll start considering each input, and then we'll classify it with the help of the assumed weights. Initially, the weights are zeros. So now for the input 121 comma 16.8, the desired response is +1. Let us calculate the actual response. Yk is equal to sigma of x0 w0 plus x1 w1 plus x2 w2. How this came? This is the formula. X0 is 1. X0 into w0 plus x1 into w1 plus x2 into w2. And this is the value from neuron, which will be passed to activation function. Okay, so because all the w's are zeros, all the terms are going to be zeros, sigma of 0 is going to be +1. And the actual response, the desired response is +1. The response from the neural network is also +1. They are same. Therefore, there will be no change in the weights. Okay. And second input 114 comma 15.2, again it is going to be 0 plus 0 plus 0. Expected, that is desired response is +1, and the calculated response is also +1. So neural network is working fine for the first class of fruit. So no change in the weights. And we'll consider 210 comma 9.4 now, the second class, second category of fruit. For this also, we need to calculate 0 plus 0 plus 0. It is now +1. Actually, the desired response is -1. Now the actual response from the neural network is +1. Therefore, there is a change in actual response and desired response. So we need to update the weights. Okay. So new weight W0 is calculated as old weight W0 plus eta 0.5 into desired response is -1 minus actual response is +1. Okay. So -1 minus of +1, it is going to be -1 into x0 is always +1. So 0 plus 0.5 into -2 into 1, it is going to be -1. Similarly, W1 will be calculated. W1 plus eta into desired response minus actual response into X1. This time we will consider the old weight is 0 for W1 as 0.5 is fixed learning rate into minus 1 that is minus 2 into X1 is 210. So we calculate it. The result is minus 210. Then W2 is also updated. It becomes minus 9.4. Okay. So after this, the new weights are minus 1, minus 210, minus 9.4. And we'll continue with the next input 195, 8.1. We calculate it with the help of new weights which are calculated. So minus 1 plus 195 into minus 210 plus 8.1 into minus 9.4 is equal to minus 1. The desired response is minus 1. The actual value calculated is minus 1. Therefore, neural network is working fine for the fourth input. There will be no change in weights. So after the first iteration, W0 is minus 1, W1 is minus 210, W2 is minus 9.4. And step 3, we will again continue the process. The reason is uh, the weights were updated and we need to test for the updated weights whether all the inputs are properly classified again. When all the inputs are classified in a particular iteration, then we will stop the process. Okay, so we check again, starting with the first input vector 121, 16.8. Now, if you calculate it according to the previous weights that are updated, it gives minus 1. The desired response is plus 1, but the actual value is now produced by the neuron is minus 1. There is a change in desired response and actual response. So we'll update the weights by using the same formula. W0 is equal to W0 plus eta into desired response minus actual response into X0. So this gives us 0, and W1 is also updated as minus 89. W2 is also updated. Now it is 7.4. We'll continue with the process by considering the second input vector 114, 15.2. It is calculated as minus 1 over here, but actually desired response is positive 1. So we need to update the weights again. W0 becomes 1, W1 becomes 25, W2 becomes 22.6 now. Next input from class 2 is 210, 9.4. It is giving plus 1 over here after calculation, but actual desired response is negative 1. So we need to update the weights again. Use 0, minus 185, 13.2. And for the next input from class 2, 195, 8.1, it is giving minus 1. The desired response is also minus 1. So there is no change in the weights. So after the second iteration, the weights were 0, minus 185, 13.2. So because weights were updated in this iteration also, we need to test again. We'll continue with the next iteration. We'll consider every input vector again and let us see whether for each input vector the neuron, the perceptron, is producing the desired response properly or not. So we'll consider 121, 16.8 again. It is giving minus 1. The desired response for this class is plus 1. Therefore, we need operation of weights. Weights were updated by using the same formula. It is now 1, minus 64, and 30. Okay. For the second input vector from class 1, it is 114, 15.2. Is also producing negative 1, but actually the result response is positive 1. So we need updation of weights. Gives 2, 50, 45.2 after updation. Let us check for the class 2 inputs 210, 9.4. It is giving positive 1. Desired response is minus 1. So you require weight updations over here. So it gives 1, minus 160, 35.8. And for the fourth input vector from class 2, it is calculated as -1. The desired response is also -1. So we'll proceed with the same weights calculated for the previous input vector. So that is 1 minus 160, 35.8 will be forwarded. We need to consider the next iteration also, since weights were updated in previous iteration. Start again by considering the input vectors one by one. For 121 comma 16.8, it is still producing -1, so we require updation of weights. It is calculated as 2 minus 39, 52.6. For 114 comma 15.2, it is also producing wrongly still. It is -1, but our desired response is +1 for the first class of fruit. We need updation of weights. This will give us 375 and 678. For 210 comma 9.4, it is also wrongly calculated. It is +1, but the desired response is -1, so you require updation of weights. These are now 2 minus 135, 58.4. And for the fourth input vector from class 2, it is calculated as -1. It is calculated as a proper, that is a correct classification. So -1, therefore you require no updation of weights. And since our weights were updated in previous iteration also, continue with the next iteration. 121 comma 16.8, it is still wrong, -1. We need to produce, the perceptron need to produce +1. Therefore weights need to be updated again. So 3 minus 14, 75.2 are the new weights now for the input vector 121 comma 16.8. Second input vector 114 comma 15.2. Perceptron is still producing wrong classification for this also. So you require updation of weights. After using these formulas, it is producing 490.4. 210 comma 9.4, this has to be classified as -1, but the perceptron classified it as +1. So wrong classification, so you require updation of weights. Now the weights are updated as 3 minus 110 and 81. The next input 195 comma 8.1 is properly classified. Desired response is -1, and perceptron classified it as -1. So you won't require any weight updations over here. Okay. So we'll consider the weights updated previously. They are 3 minus 10, 110 comma 81 for the next iteration also. So we need to continue with the next iteration also. Since weights were updated, now it is 121 comma 16.8. Now it is -1, wrongly classified. Update the weights. It is 4, 11, 97.8, the new weights. Okay, and so on. If you continue the process like this, somewhere you will get weights. W0 is equals to 50, W1 is equals to -30, and W2 is equal to 300 after performing few more iterations like this. Okay, so once you get to these values, W0 is equal to 50, W1 is equal to -30, W2 is equal to 300. Let us check for all the inputs whether the perceptron is classifying the correctly or not. So for 121 comma 16.8, the value produced is +1, so it is properly classified. Desired response is +1, it is producing +1 here. And for the second input vector 114 comma 15.2, the desired response is +1, now it is producing +1, so it is correctly classified. And for the class 2 sample 210 comma 9.4, desired response is -1, and the perceptron is producing -1 itself. And for the fourth one from class 2 195 comma 8.1, desired response is -1, perceptron is producing -1. So you can see that for all the input vectors, the desired responses and actual responses are same. That means your perceptron converged completely. It is working fine for any given input vector. For all the samples, it is producing correct classification. Therefore, perceptron uh, is properly designed. Now we can make use of this perceptron to predict the class of any given fruit. Okay, so it is given in the problem that a task is given. The task is to identify the class of a food where series. So the task given is identify the class of food with weight 140 grams and length 19.7 centimeters. Okay, it is not actually there in the given input samples. It is a new sample, and it is asking. They're asking us to identify the class of this particular food based on the uh, perceptron. Okay. So we already designed the perceptron, and now we will send this 140 grams and 19.7 centimeters as input. Okay. The weights are the final weights are minus 30 and 300 here, 50 for the bias weight. Okay. Now the calculation is yk is equal to 1 into 50, that is 50, plus 140 into minus 30 plus 19.7 into 300. So it gives us some positive value. If a positive value is given for signum activation function, it gives us a plus one as classified. That means the given fruit with weight 140 grams and 19.7 centimeters length belongs to class 1 fruit. Okay, so that is how perceptron can act as a pattern classifier, uh, which is shown in this example, right? So that is how we can design perceptrons and use them for pattern classification problems. Uh, so till now we learned how a perceptron can be designed and how to test it, how to use it for classification problems. Here is an exercise for all of you. Uh, Design a perceptron model for classifying the output of OR gate. So we all know that OR gate truth table is like this: 0 0, the output is 0; 0 1, the output is 1; 1 0, the output is 1; 1 1, the output is 1. And if you observe the outputs, there are two classes of outputs. One is 0 and the other one is 1. So group it as 0 as class 1 and 1 as class 2. Give them plus 1 and minus 1 desired responses. And it is again the same approach you need to follow, which is used in previous problem. Okay. So this is an exercise for you. Design a perceptron for classifying the outputs of arcades, assuming this truth table and the two classes of outputs. Okay, I hope we'll do this. Uh, so that's all for today. We discussed about what is a perceptron, and then we have gone through how a perceptron convergence algorithm can be used to design a single layer perceptron, and then how it can be used uh, as a pattern classifier, and then after designing how it can predict any given input and classify it into some response. Okay, so that's what I want to discuss today. I wanted to discuss today. I hope all of you understood the topics. Thank you all for your patient listening. In our next session, we'll start with what is a pattern classification. We'll go through some examples, and then we'll discuss about the naive Bayes uh, classifier in our next session. Thank you all. See you in next session.